You can start, sir.
Yeah, so let us start. So welcome everyone. So this is the third and final lecture from my side, and as I already told you that today I will be talking about what are the different applications of these precision or precise atomic clocks. And there are two different sectors where they are basically used. One is technological applications in sophisticated technologies for precision time keeping there, and also probing fundamental science. So in this lecture, I will be covering three parts particularly. One is technological applications of the atomic clocks. Second is how these clocks can be used for studying fundamental science. And at the end, I will spend few slides to explain what we are doing at IUCAA, what we are planning. So this lab, what we are building is called Precision and Quantum Measurement Lab, PQM lab in short form. So I will spend like 3-4 slides on what we plan there. Okay, so let's begin. So I told you that over last 100 years, how this clock, particularly the atomic clock, have evolved largely from 1945 to until now. And over, if we look into this last 100 or 120 years time scale, it has evolved from free pendulum clock to like based optical clocks. So I already discussed in my last two lectures about the microwave clocks. These are like fountain clocks and beam clocks. And the best fountain clocks have reached to an accuracy of 10 to the power minus 16, fractional accuracy. And this cesium beam clock basically started since 1967 and so, and then in between laser cooling and trapping was developed, and then it became fountain clock. I mean, it was modified to a cold atom based fountain clock. And as you see in this plot here, how the accuracy of these cesium clocks from hot atom clocks to the fountain clock, how it has changed. So it started here, and then it has become almost like nearly sub nanoseconds, or actually, yeah, much smaller than even nanoseconds at this moment, or even actually much better than nanoseconds, using these laser cooled cesium clocks. I also discussed about the optical clocks, which have reached to few parts in 10 to the power minus 19 frequency, and these kind of clocks are basically at this moment used for studying fundamental science. And I will discuss about the applications today, as I said. So this also I showed yesterday, like what are the present scenario of the accuracies of the different optical clocks. As you see, it has reached to few parts in 10 to the power minus 19 using both neutral atom lattice clocks as well as trapped ion clocks. And let us start with their applications. Why do we need for that? So let me begin with a very simple application which all of us, I am very much sure that all of us use, that is Google Map. But do we ever understood how the Google Map works? Maybe. I mean, I hope that many of us already know about that, but let me begin with that because that is very simple to understand. So basically, our mobile devices have internet connections and it has GPS receivers inbuilt there. So let's say you are somewhere you lost somewhere. I don't know from where you are. You may be from Pune, from Delhi, whatever it is, wherever it is. You lost somewhere. What do? We just start the Google Map, and then it automatically finds where you are and where you want to go. If you plug it in, it gives you the route. How it works. So actually, the backbone of this entire thing to work is time synchronization. GPS receiver is receiving only the signal. It's only a receiver. But the way it works is actually perfect, or not perfect, actually nearly perfect time synchronization. So let's say you are lost somewhere. You have started your navigation systems. What happens? Your mobile device, or let's say any navigation systems, your handheld instrument have the receiver. It receives data from its nearest transmitter. We know. I mean, you have seen these mobile antennas here and there, sometimes on roof of some buildings and so on, so on. So these are actually the transmitters. So your mobile device actually receives data from the transmitter. So what happens when this transmitter sends a data packet? It gives a timestamp. Like at time, let's say T1, it is sending the data, and at time, let's say T end, let's say TS and TA. T start is the starting time, and when your mobile device receives this data, then it also first gives a timestamp. Let's say this is TE, T end. So this TS minus TE is basically the travel time of this data packet. It's traveling at a speed of light. So this T1, what you see here, it's basically travel time of this data packet from the transmitter to your receiver. And since the data packets are traveling, it's an electromagnetic wave, so it's a traveling at a speed of light. So multiplying this T1 with speed of light, your mobile device can calculate at what distance this transmitter is. So C times T1 is, let's say, D1. So your receiver will be able to say that he or this receiver is at a distance D1 from the transmitter, but it can be anywhere in the circle. If you consider it's a two-dimensional thing, then this receiver can be anywhere in the circle with a radius of D1. So it cannot give a position yet. So you can only say I am at a distance D1, but I can be anywhere in a circle where the radius is D1. Okay, so far so good. So then actually what it does, this receiver receives data from multiple transmitters. So let's say there is a second transmitter also, it transmits data. It also does the same thing, like gives the timestamp and receives it. Then it also calculates the distance of the other transmitter, which is, let's say, at a distance D1, D2. So then D1 and D2, if you consider two circles, they can only interact only 2 points. Two circles can interact only in 2 points. And then if you have two transmitter and one receiver, then you can say either you are in this intersection point or that intersection point. So now from an entire circle, you have reduced your spatial position to 2 points. You are either in this point of the intersection or that point of the intersection, but yet these 2 points can be very, like, several, even thousand, I mean, just have several kilometers away. So that's also not helpful. So you need another transmitter. So what happens if you have a third transmitter and your receiver does the same thing? Then these three circles can have only one intersection point. Yeah. So now this was a two-dimensional picture, but the world is actually in 3D. So that's not a circle, but it's actually a spheroid. Yeah. So you need actually 4 receivers so that your mobile device can work. So just only having one receiver and one transmitter and one mobile device, it won't give you position, it won't actually work. So sometimes that's why you see that you have a mobile phone and you will see that your mobile phone is not getting tower. We see this little single lines, 5 lines, small to little bit larger, and we don't get connection and we don't see, there is not enough signal. It actually means it's not able to connect with 4 transmitters at the same time. It may be connecting with 1 or 2 or 3, but until and unless you have minimum 4 number of transmitters, your mobile device can connect at the same time, it won't work. So that's what it means. So that's how a navigation systems in your device or on your Google map, that's how it works. Now let's see. So basically then there is one requirement. So all these transmitters and receivers, they must have clocks so that they can give the timestamp. But all these clocks have to be synchronized, else it will not work. So let's take a simple example. Let's say this clock and this receiver clocks are not exactly synchronized, but they are having some time difference, delta t. So then you will not be able to find out your positions exactly, but you will have some kind of error bar of your position measurement. And let's say this is what I mean, this width of these circles, instead of a single line, this width means what is the error bar that your receiver can detect for your position. And this error bar will be larger as you have larger and larger error in the time synchronization. So let's say if the time synchronization is accurate by 1 second, so imagine, I mean, just consider that data is traveling at a speed of light, c 3 times 10 to the power 8 meter per second. So for 1 second inaccuracy in time synchronization, you will be able to measure your position inaccurately by a distance 3 times 10 to the power 8 meter. So you will not be even in this world. Just 1 second. 1 second is a very simple thing for a normal life. Yeah, so 1 second inaccuracy will measure your position by a inaccurately by a distance 3 times 10 to the power 8 meter, which is huge. So that means you can now understand what level of time synchronization is required just for your mobile device to work, which we all of us use nowadays, but we don't realize that what is inside of it or how accurately these things have to work. Yeah, so for example, if you want to measure your position with an accuracy of 1 meter, yeah, then you need 3 nanosecond inaccuracy of the, you can afford maximum 3 nanosecond inaccuracy in the time synchronization. So you might have seen that you want to go to some place, let's say some restaurant, and your Google map navigates, and then maybe you will end up to very much close to like within 10 meter accuracy or so, or 30 meter accuracy. So if you just consider, let's say 30 meter accuracy, that means something like 100 nanosecond time synchronization you can afford. So for this kind of inaccuracy, accuracy level, you obviously need an atomic clock. The simple pendulum clock or quartz clock won't work. So this is a simple way to understand why atomic clock is very much important. And for any sort of time synchronization or anything, this is how it works, because all the data goes through electromagnetic waves, and they all travel at a speed of light. So let me just convince you through another way. Maybe you have already traveled through aeroplanes, and probably you have noticed that, maybe you have noticed or maybe you have not, but those at least who have noticed it, like while an aeroplane takes off or lands, then it's always in an like manual mode. Pilot controls the flight. But when it is in the flying, when it is flying in the air, then it's maximum times it's in the autopilot mode. Just think about it, why it is. Why while during the landing and why during the takeoff, the flights cannot be in the autopilot mode. The reason is typical width of runway is, let's say, around 25 to 30 meter. Depends on which runway it is, obviously. So if the time synchronization is, let's say, within the accuracy of 30 nanosecond, and it's in, that means you can detect your runway position with an accuracy of something like on the order of 100 meter or so. Yeah, something like few tens of meters or 100 meters. So that means you will not be able to detect your runway properly. That's the entire reason why the flights during the takeoff mode or during the landing mode, it's always in the manual control. But during the flight, 10 meters or few 10 meters, who cares? It doesn't matter. Any of the flights are not going that close. So it can be easily in the autopilot. Well, it's not that simple, but it's a simple analogy to understand. There are many more things, so you can do little bit more corrections and bring down this 100 meter to maybe 10 meter, but on that order. So it's a good way to understand these things. Yeah, so this is the simple example of time synchronization in technologies. Time synchronization, I'm not going into the fundamental science yet. So that's why the time synchronization or atomic clock or timekeeping is very, very important for any developed or developing countries who wants to do sophisticated technologies, even simple ones like mobile phones and navigation systems. There are several others which requires very accurate time synchronization, and many of them actually we use in our daily life, but we do not realize. Even like we take out the money from ATM machines, and it gives, if you have read this small this thing which comes out after taking the money, that have a timestamp, and you will see that this if you see it carefully, it will have a timestamp up to seconds accuracy, but actually internally in the machine it has much accurate time steps on the order of milliseconds or even better than that. And it's very important for protecting from the fraud and etc. etc. I won't go into those details because those things will be a complete separate lecture. But let me give you a few examples where this kind of very accurate time synchronization is, I mean, without that it won't work. One is obviously navigation, I told you. Then communication systems, all the communications are radio frequency or optical communications. For that purpose, for the similar reasons, accurate time synchronization is very important. Surveillance, it's a national security for anything. For very accurate targeting, like for sending missiles or putting the satellites into their proper orbits and etc. etc. Accurate time synchronization. Without that, it won't work. Internet of Things, Industry 4.0. Industry 4.0 is basically the new next generation industry, which is completely automated, which will be based on artificial intelligence, machine learning, and all these kind of things, based on Internet of Things and so on, so on. So when we are talking about this Internet of Things, it will obviously require very accurate time synchronization. Cyber security, digital archiving, as I told you, like this ATM slips and so on. International trade, for example, these stock markets, they require actually very, very accurate time synchronization, much accurate compared to milliseconds or even microseconds. Imagine like this is like a trading. Yeah, it's like something like there are several people who are trying to buy the same item, and whoever comes first or bids first, he will get that. It's an international open market. Millions of people are trying for the same thing. So it has to have very accurate time synchronization. Otherwise, just even though let's say you want to buy something at higher price, but because your time synchronization is not perfect, so you can miss it by fraction of a second. And that's why all these stock markets, they are very accurately time synchronized with respect to atomic clocks. Even our Bombay Stock Exchange or everything is having accurate time synchronization with atomic clocks, and even with the National Metrology Institutes of the country in many places. For example, in NPL UK, they are providing extremely accurate picosecond, few tenths of picosecond accurate time synchronization to their stock exchange, which is, I don't know, maybe 60 or 70 kilometers away from their metrology institutes, or I think 200 kilometers, I forgot exactly. So weather forecasting. So for weather forecasting, basically how it does, the satellite takes picture and then looks into the dynamicity of these changes of, let's say, cloud or cyclone and etc. And these pictures, they have to be time synchronized, or they have to have a very accurate time stamp basically, so that they can find out how fast the cyclone is moving and etc. etc. So for all those things, you require very, very accurate time synchronization. Else, like you can calculate, like let's say cyclone thing is moving with a velocity of 200 kilometers per second. So if you just miss it by, let's say, even fraction of a second, let's say half a second or something like that, then you will basically miscalculate the position where the cyclone will hit by several tens of kilometers. So it won't work. So, sorry, did I say 200 kilometers per second? It's 200 kilometers per hour. So, so for that purpose, you actually need quite accurate time synchronization for weather forecasting also. So there are several examples. It won't be possible to give you all the examples or read through all the examples. But from these technological applications, I gave you one example, that is this communications, which is one of the easiest example, let's say, to understand. Now, like the another last thing of this sector is like our ISRO is building the IRNSS, Indian Regional Navigation Satellite Systems. They have 7 satellites on board, and each of these satellites have onboard rubidium clocks, and they have to be also very accurately synchronized, and they are all synchronized with National Physical Laboratory, Delhi. The primary time scale, they are having the primary atomic time scale and etc. So they are synchronized with that with an accuracy of a few nanoseconds, I think on the order of 10 nanoseconds or so. And that is very important to this entire IRNA system to work. As you see here, so this is highlighted, this yellow part. So they claim that they want to be accurate. They want to detect the position in India and subcontinent of India with an accuracy of 20 meter, and 20 meter means typically 7 nanoseconds. So their time synchronization have to be better than 7 nanoseconds. Then only they can achieve that, the entire system. And it's coming from NPL India, the time synchronization. Okay, now I am moving to the second part, that is the applications of these clocks for fundamental science. And they are basically, these optical clocks are the major player compared to the cesium fountain clocks. So basically the cesium fountain clocks won't have enough accuracy to do these fundamental science experiments. In fact, these optical clocks are also kind of in an still it needs improvement. So somebody was asking like, where is the like, where do we stop? There is actually no stop. I mean, we have to still improvement. As you improve, you detect more, you detect things more precisely, or you're basically, let's say, sensitivity of the detections becomes much better and better. So like 10 years back, this kind of fundamental science experiment using optical clock, I mean, at that time, optical clock was not there. So using atomic clock was a dream. People were not able to do that because the microwave clock didn't have the sensitivity, enough sensitivity for that. So 10 years back, for this, let's say, list of fundamental science experiment, people were only doing through astronomical sectors, or maybe some of them through high energy sectors. Yeah, but they are good, very extremely good, but not as precise as optical clock can do. I will show you those things. So, but now we have the optical clock. It can actually do more sensitive measurements of the same similar things, and it will further improve, and we will be able to do probably even much better things. And why it will improve? Because now the quantum phenomena based technologies are coming. Yeah, so those things will be incorporated and so on, or maybe something else will come. That also we don't know. Maybe even not the optical clock, maybe something else, completely some other new technology will come. But even for the optical clock technology, or even in the astronomy also, new quantum phenomena based things are coming one after other, and then it's basically improving the sensitivity of the measurement techniques. Yeah. So some examples are, let's say, finding out constancy of the fundamental constants, like let's say electron to proton mass ratio, or fine structure constants, and so on. Constancy of the fundamental symmetries, like let's say Lorentz symmetry and so on. These are fundamentally constants of symmetry as per our standard model. But there is no hard and fast rule that our standard model is really perfect. So there must be, it can have something which we do not know. So it's important to find out those flaws if there are any, and etc. And in fact, there are theoretical models which says it should not be, there is no reason it has to be constant. So it's better to find out whether they are really constants, or if they are dynamic, at what rate of change it is changing, whether it matters or not matters, well, in a scientific way, of course. Then other examples like geodetic measurements, quantum geodesy, what we call, or quantum metrology also. Then searching for dark matters, even gravitational waves, which we nowadays is done by LIGO, or let's say microsun interferometer, LIGO, Virgo, and so on. But there are proposals that atomic clocks can actually do this GW measurements if you have constellation of atomic clocks in the outer space. Yeah, so someone was asking what will happen if the atomic clocks is placed somewhere in the other part of like outer space and etc. So those kind of experiments have been proposed. It's very challenging, so it has to go step by step. And the steps are like, first people build the atomic optical clock in laboratory. Then they are trying to build it transportable, so that you can, it's still big, but you can still transport it. Then one have to make it space qualified. That means something can be put it on a payload, so that you can put it on space. Then you have to consider to make a constellation of atomic clocks in space, or maybe outer space, or even maybe in Moon or Mars, and so on, so on. So these are all things which progresses step by step. Nothing happens in one day, or even in a time scale of 10 years. It takes long time to do all these technological things step by step. And today this is in proposal, but maybe like 10 years from now, this will be actually in reality, because 10 years back, there are many things which were only in concept. People never thought that, well, obviously they have thought, but they are all in dream that this kind of experiment will happen. But nowadays, today, those experiments are actually happening. So there is actually, what I'm trying to say, infinite scopes to work in every field, of course, but in this field also. So let me start with, I'm trying to give 2-3 examples here about the fundamental science, how the atomic clocks can do better job here, or can be used here. I don't have time to go into all these to cover all these examples, but I will try to cover 2 or maximum 3, depends on how much time permits. So let me start with this local Lorentz invariance violation. Lorentz invariance is it should be invariant as per the our known laws of physics. And Lorentz invariance basically means any laws of physics has to be independent of reference frame. If you are in different reference frame which are moving differently, or something is stationary, something is moving, something is rotating, etc., the laws of physics has to be constant. It should be same in all reference frame. What if it violates? If it violates, that means your measurements, some measurement quantity will be different in different reference frames, which is obviously seems not the right thing, but nobody knows. I mean, might be that's what it is. So the other thing, what happens, if the Lorentz symmetry violates, then CPT symmetry. CPT is considered, CPT means, C means charge conjugation, P means parity, and T means time reversal symmetry. So altogether, all 3 symmetries, like if you do charge conjugation and if you do parity symmetry, like going from particle to antiparticle, then take a mirror image for the parity, and then going to reverse in the time, that altogether means CPT. If you do a CPT transformation of something, it has to be symmetric. That is as per our standard model. If that violates, then there is a big flaw in our standard model. Individually, parity and time reversal symmetry has already been found out, they violate. But together, altogether, 3 of these 3 things, this is considered as a very good conserved quantity in our standard model. But if Lorentz symmetry violates, then CPT, that means CPT symmetry also violates. So that is another important. So Lorentz symmetry plays a very important role in our known knowledge of physics. So it's very important to know whether it's really symmetric, or it's violating, or its symmetry gets violated. And if it gets violated, then we have to rethink of our standard model. So that will tell us the known standard model is not enough. We have to have an extension of the standard model. So that's another I mean, completely altogether a different story. We don't know what will happen. But what we are trying to do, basically, we are trying to do a measurement of CPT violations, whether it is violating or not violating. So this picture, what you see here, is cosmic microwave background. That's considered as the stationary frame of our universe. The average temperature of CMB is 2.73 Kelvin. We know about that thing. And what you see here, it's a different times, different telescopes have taken the pictures of the CMB, and the resolutions get better and better. So I'm not a CMB expert, obviously, but let me tell you why I am showing these things. This is a rest frame of our universe. Now, within this rest frame, our Earth is rotating. Well, of course, this is not a 2D scale picture. It's only for telling you the entire concept. So don't go into the scales. So Earth is rotating. So Earth is a rotating frame with respect to this CMB reference frame. And also Earth is rotating around the Sun. So it has 2 different rotation frame of rotations. So if you can do a measurement in the reference frame of Earth, and if you can do a measurement in the reference frame of CMB, and if you can show there is a difference, it has to be very sensitive measurement, of course. If you can show there is a difference, that will tell us like whether Lorentz symmetry is violating or not violating. If it is violates, then you will get two different measurements. But how can you do that? There is no way at this moment with the present technology you can do a measurement somewhere in a different reference frame where you don't have any influence of Earth. At least at present you cannot do that. Yeah. So so what we can do. Let me tell you what we can do or what people have actually done. So assume that there is a frame dependency on energy levels of atoms. Then this interaction between two reference frames will give you a perturbation of the energy level shift, and that can be written for the now if you do little bit more mathematics, which of course I am not going to do here, but if you do little more mathematics, you will say like if you have two different states for a clock transition, and these two states will change slightly due to this reference frame dependent interaction with the atomic reference frame, and that will in totality will give you a slight shift of the transition frequency, and that you can write in terms of C. It's a tensor, second order tensor, and T, which is again a second order tensor, two matrix elements. Now this C is basically it's called C mu nu coefficient, so it basically connects two different reference frame, and it's a second order matrix. And T depends on the atomic properties. It tells like a particular atom or a particular energy state, how sensitive is that to this reference frame dependency. Well, I am actually speaking very generally. I'm not going to deep of all these mathematical things, but that's what it says. Now, let's say on Earth, you have two atomic clocks, very precise as atomic clocks. Maybe they are just located next to each other. They are identical in nature, but their only difference is they are oriented differently. Their quantization axis is different. So I am representing these two accurate clocks by these two cats, and the tail of the cat is telling me the direction of the clock. Yeah, so this clock is like upside down, and this clock is in the horizontal plane. So since everything else other than this direction, they are identical, so the only thing they will have different in the C mu nu coefficients, because with respect to the CMB frame, they are oriented differently. So let's say for this clock, this C mu nu coefficient is C mu nu 1, and for this one, this is C mu nu clock 2. So since everything else is same for these two clocks, only over the time as the Earth rotates, these two coefficients will be different. So basically, this differential of these two coefficients, C mu nu 1 for clock 1 minus C mu nu for clock 2, this differential quantity will change over time due to this rotation. So basically, if you have these such clocks, and if you measure the frequency, their frequency ratios very carefully over time, if there is really a this reference frame dependency, then you will see slight changes between these two clocks, even though rest of the things are identical. And people have done that measurement in PTV in Germany. They have ytterbium ion clock, two ion clocks just sitting next to each other, but only the quantization axis, that is this red arrow, direction of the red arrow, they are different. And they have done this measurement exactly in the way that I expressed you. And they tried to find out whether there is any dependency on the reference frame. That means whether this quantity is there any change or not. And ytterbium ion is a very good candidate for that, because this T coefficients, which depends on the properties of the atomic states, that is largest for ytterbium ion clock transition. It's minus 135 compared to any other optical clock. So that's very sensitive. That has largest sensitivity, largest known sensitivity, let's say. for doing this experiment. That's why they have done it with ytterbium ion. And what they found an upper limit of the sensitivity of their experiment. Yet they did not find any violations of the Lorentz symmetry, but they could only say what is the sensitivity level of their experiment. And that's what it says here due to this atomic clock comparison of ytterbium ion clocks. And you see there, these are actually different coefficients of this semi-Newtonian tensor. And these are all on the order of, the best thing is on the order of 10 to the minus 21 or 20 level, and few of them are a little bit in the lower side. There are also other experiments, like as I told you, astronomy and high energy physics experiment, they basically look for same fundamental physics. Here you can see there is another experiment on calcium ion. That's not a clock experiment. They also tried to measure it with their experiment. This is looking into microwave transitions, very accurate measurement of microwave transition in dysphorium atom. And this is by looking into quasar absorption spectra in astronomy. All of them, they basically tried to measure what is the value of these C mu nu coefficients, and all of them gave an upper limit of the sensitivity of their experimental techniques. So far, there is no experimental validation of values of this quantity, but only higher limit of their measurements. And you can see from their this order exponents, clock frequencies actually gives the best result so far. It's on the order of 10 to the power minus 20, whereas these two are 10 to the power minus 17, 18, and astronomy is 10 to the power minus 15. So don't go with the numbers here, but the point here is all of us, different experimental sectors, are trying to find out answers for the same questions through different techniques, and something is more sensitive and something is less sensitive, and over the time this changes, and etc. etc. And atomic clock, optical atomic clock, plays a very important role to find out answers for those things, and etc. Okay, so now I'm going to the second example, which is whether, so the earlier one was symmetry, fundamental symmetry. Now I am going to the fundamental constants. So whether fundamental constants are really constant or they are changing over time at a very, very, let's say, negligible rate, infinitely small rate. So that question was first asked in 1967, whether the fine structure constants, alpha, fine structure constant for electromagnetic interactions, alpha, is really a constant or it's varying with time. This is a physical review letter paper, and that's only a single page, one page physical review letter paper. Yeah. So they did something with astronomical spectra at that time, and they say even if it is changing, it's a rate of below 10 to the power minus 12 per year. From their some experimental observations and etc. But over the time, the experiment has changed a lot. Then in 1999, from Australian group, New South Wales, from University of New South Wales, there is a theoretical group who said that if you can measure the redshift of quasar absorption spectra, then you can actually detect this alpha, time temporal constancy of the fine structure constant. And in the same year, from the same university, there is an experimental group who actually published one paper on those things, like values from quasar absorption spectra. I will come back to those things, but they were. I will come back to the experimental results. So let us try to understand what this alpha violation means, why it should violate. So alpha, the value we know 1 over 137, precisely this is this much from the core data. The alpha is E square divided by 4 pi epsilon naught times 1 by h bar c. And you see here, just a second. You see here, all the quantities are actually constants. So that means alpha has to be constant. To best of our knowledge, all these quantities are constant. And the dimension of the first quantity is just inverse of the dimension of the second quantity in the second bracket. So that means these dimensions will cancel out each other. So alpha is a dimensionless fundamental constant. So here I have considered actually phi 0, which is magnetic flux by due to spinning of a electron. Electron is a charged particle, and that will have two components. You can write it as a two component, which is the magnetic part and the electric part, phi m and phi e. It's just a notation basically to write it down in this way. Now, if I just take the second constant part, like Planck's constant times velocity of light, hc. So I have written h bar c in the form of E phi naught. Phi naught is this magnetic flux divided by pi times 1 over square root of mu naught epsilon naught. Mu naught epsilon naught are the free space permeability and permittivity. Then I have written this entire quantity in terms of phi e and phi m, which are written like here. So now if I take a log on both sides and take the derivative of it, then you can easily see that this is basically can be written as some constant times delta phi e by phi e plus delta phi m by phi m. So if hc is a constant, both of them are constant, so you know that, yeah, then this entire quantity has to be 0. This quantity within the bracket has to be 0. Yeah, okay, so far so good. Now let me take alpha. I am taking this entire quantity alpha. Then I do basically the same thing. I write alpha in terms of phi e and phi m, and if I do the same derivative thing, then I will get delta alpha by alpha is equals to some other constant. It's not the same constant. Other constant times delta phi e by phi minus delta phi m by phi m. So there is a negative sign, there is a positive sign. Both of them are constants. So that means this quantity has to be 0 as well as this quantity also have to be 0. So if I do that, if I take this one, then delta phi e by phi e is equals to minus delta phi m by phi m, and it's basically, it's very convincing because total energy has to be conserved. So that this means there is a conversion of electric to magnetic energy or magnetic to electric energy, but total energy has to be conserved. We know that, fine. But what if alpha is constant? If alpha is constant, so okay, if this is true, then delta alpha by alpha cannot be 0 because then this is not a 0 if I put this value here. Or on the other hand, if I take this part is 0, if I consider alpha is constant, then this thing is not is equals to 0. So that means violation of the conservation of the energy. So something else is happened, some quantum field, some ghost quantum field or something is there. So we don't know that thing. Both of these things can happen, but we don't have an answer yet to that. So it's very important then to find out whether alpha is constant or not constant. Yeah, through experimental verifications of that thing. So what can we do? We can use atomic clock for that purpose. Okay, so energy level, well, in atomic clock, I have already explained to you, basically we are measuring a clock transition frequency between two energy levels. So the clock transition frequency we measure very, very precisely. Now let me come back to one step back, energy levels. So here I have written the energy levels, and you have read it from your BSc and MSc, like this Bohr's theory, Sommerfield's theory, Pauli's corrections, and so on, so on. So if you can, even there are many more. So if you can write this, first part is basically this Bohr, Sommerfield, and and then second part is relativistic corrections. Okay, second part is relativistic corrections and quantum electrodynamic contributions, and third part is isotope shifts or different size of the nucleus. If the size of the nucleus changes because of the neutron numbers, then also that will change the energy levels. So these are, and even there are many higher orders also. I'm not going into higher than this. So this part, this second part and the third part, they are actually having this alpha term at different orders. So the first part, that is this non-relativistic contribution of an energy state of an atom, that is actually maximal contribution. It's like 99% or so. But these remaining, let's say 1% or less than 1% or very small fraction of the entire contribution is the small corrections, very small but non-negligible corrections. You cannot neglect them for precise measurement like clocks and etc. And they, for example, this part is having higher order terms of alpha, fine structure constant like alpha square, alpha cube, alpha 4 and so on so on. As the higher order goes higher and higher, the contributions become smaller and smaller. So that part I have, for simplicity, I have written alpha square times some function of alpha. Yeah, and that is actually most important part what I'm going to discuss next. So let's say I have this clock transition, which is making this transition between two energy levels, down state and some excited state, and the clock frequency is WCLK clock, and the energy corresponding to that is delta E. Okay, so then I can write delta E is equals to WCLK clock times Planck's constant, h nu basically, and that I can write in terms of Rydberg constant, R alpha times CH, again constants, velocity of light and Planck's constant, times some function of alpha. Yeah, alpha is fine structure constant. If I take a time derivative of that, you can simply write it in this way. And then this part, I mean, let's consider this is a constant, so that becomes 0. Assume this is a constant, we know to best of our knowledge this is a constant. So then this remaining part, I can write f alpha is like alpha square plus alpha cube plus something something something. So that you can write some sensitivity parameter times delta alpha by alpha. Finally, you will end up to that. And this sensitivity parameter will depend on atomic properties. For a particular atom, this may be this alpha square, alpha cube, alpha to the power 4 and alpha to the power n dependency is large. So your sensitivity will be very large to alpha for those atoms. And for other atoms, that may be smaller. So here I am comparing few neutral atoms and few ions which are potential candidates for clocks. I already discussed about this. I already showed you a table yesterday about different optical clocks, and these are the elements basically. And here the calculated sensitivity of these atoms are written for these alpha violation measurements. This is this sensitivity basically. And you can see that ytterbium ion has the highest sensitivity compared to any other known atoms and ions. Yeah, so ytterbium ion is a very good candidate for this this type of fundamental science measurements. So, for example, this is ytterbium and this is strontium. Strontium is nearly negligible sensitivity. So, if I let's say have two clocks, strontium clock and ytterbium clock, strontium neutral atom, optical lattice clock, and ytterbium ion trapped in an ion trap clock, and they are very precise measurements of the clock transitions we can do. But over long period of time, the strontium will stay almost constant with, the change will be very small because the sensitivity of alpha dependent sensitivity is very negligible compared to ytterbium. So if you can compare strontium and ytterbium ion clocks, strontium atom and ytterbium ion clocks over long period of time, then you will see a gradual change of their clock frequency measurement, where ytterbium ion will be changing faster and strontium atom change will be much in a smaller rate. So that's why strontium and ytterbium is a very good candidate for this kind of experiments. And if you remember, I think last time I told you that in ISSAA Pune, they are building strontium lattice clock, and in IUCAA, we are building ytterbium ion clock. And the reason is this: these two candidates can play a very good role to measure several fundamental physics things. And that's the reason we are building these two clocks building clocks for these two elements. And we want to connect these clocks via a phase stabilized optical fiber and want to do these measurements in later days. Okay. So again here, the alpha variation have already been measured by clock comparisons, and here are the few results. So ytterbium ion have 2 clock transitions, octopole and quadrupole transitions. Yesterday I spoke about octopole and quadrupole transitions, and similarly ytterbium ion with cesium fountain and mercury ion and aluminium ion, and these are the values. It's on the order of 10 to the power minus 18. There are 2 digits after the decimal points here. So these are the references. Whereas this similar alpha violation have also measured through other experiments. For example, by measuring redshift of quasar absorption spectra, and here our Indian colleagues have done like fantastic job there. Like our own IUCAA Srianand have analyzed data from different telescopes and looked into the hyperfile lines. No, sorry, this is Nisim. This one, optical transitions from quasar absorption spectra, and they gave a value of 10 to the power minus 16, but it's much higher compared to what atomic clock can give. And our neighbor Nisim Kanekar, he worked into the radio frequency regime and looked into the hyperfine splitted levels, and he also came up with this value, which is again higher than atomic clock comparisons. There are other experiments like OCLO, natural uranium nuclear reactor. There is a natural nuclear reactor in OCLO in Gabon. It's in Africa. Yeah, and naturally the abundance of uranium 235 and 237 isotopes have some natural abundances, but there the ratio of uranium 235 and 237s are different compared to the natural abundances. So since this nuclear reactor is reacting for ages, like probably millions years or something like that, yeah, so there is a model that if alpha is varying, that can give you this kind of difference in the natural abundance. So that's how people also predict that probably alpha is slowly varying. There are other experiments like again looking into the microwave transition of dysphorium and other astronomical routes, but so far, okay, this is fine. So far actually the atomic clock measurements are the best one, most precision measurements to find out whether alpha is varying or not. And it's a null experiment, so people have not found any violation of the alpha, not violation, time constancy of the time variation of the alpha, but it's only like experimental sensitivity of their measurement, and that tells that you have to have better clocks to measure actually like if there is something actually varying or not. And for that people are more motivated to build better and better clocks. So the next level is actually, I mean, connecting different clocks, intercontinental clocks. Let's say one clock in US, other clock is in Japan, connecting them together by a optical fiber. It's not a normal optical fiber, but it's a phase stabilized optical fiber. That is another level of complicacy. And by interconnecting several optical clocks throughout the world, you can actually make your sensitivity, you can enhance your sensitivity to another few orders of magnitudes and so on. And that's what actually happening. Instead, like people are not only making optical clocks, but they are interconnecting them together. That's one, for example, in European Unions. This is UK in NPL UK, not NPL Delhi. And what happened to my cursor? And this is a PTB in Germany, and this is Sierte in France. These two clocks are interconnected. These are in 3 different countries. They are interconnected by phase stabilized fibers, and they are doing this kind of high precision experiments. Okay, so I will skip this part because I'm already running late. So now I am coming to the, I gave 2 examples of the fundamental science experiments, but I am coming to this last part, last few slides. But before that, maybe I can take 1 or 2 questions if there are any. So one I see, Abhay, pulsars are known to be precision clocks in astronomy. How does their accuracy compares to the atomic clocks? See, pulsar are of course good clocks, but first thing is they can play a major role in fundamental science experiment, but they cannot be a standard. They cannot be a standard because it cannot be it cannot be detected by every country. For any standard, it has to be there in every country. So it cannot be a standard. Second thing, pulsar spins also slows down and changes. It's not a constant spin. And there are several pulsars, from millisecond pulsar to microsecond pulsar and other things. So pulsars obviously can play a major role in astronomy, fundamental science experiment, but they cannot be replaced by atomic clocks and so on. So there is a question by Utkarsh.
Good afternoon, sir.
Yeah.
Sir, could you go to the previous slide titled Accurate Measurement of Atomic Transition?
Where I'm going back, so tell me where.
Yeah, this one, sir.
Yeah.
So, sir, in this slide, you have taken delta of ln Rydberg constant into speed of light by delta t as constant. But my doubt is that the speed of light is also dependent on medium. So the change in speed of light will be very much high compared to the change in fine structure constant.
No, but this is speed of light in this formula. Speed of light is free space speed of light, which is a constant to best of our knowledge. Of course, one can say that speed of light in free space is also not constant, but then that will also have to change many things in our known model. So here, to best of our knowledge, both of these things are constant. So here the c, speed of light, is free space speed of light, which has to be a constant, right? Hi, is it okay? Utkarsh? I have unmuted you. You can speak now.
But yes, sir, that is fine. But my question is that aren't we missing a lot of physics? Because the speed of light, the error in speed of light will be more than the error in fine structure constant.
No, I don't understand why there will be an error. This is like speed of light in free space is a constant quantity. Do you agree or not? First, go step by step.
But yeah, I definitely agree, sir. But
then what is the error? So if you consider speed of light in free space is not constant, that you have bigger trouble. So then you have to go, your entire standard model physics is completely then washed away. You have to try something new. See, I am not saying by this formula, I am not saying that speed of light is not constant. I am assuming speed of light in free space is constant. So this part, I am just simplifying, cancelling, and I am saying that I am now sensitive to this part. Speed of light, to best of our knowledge, is a constant thing. Sorry, you are again muted. I don't know why you are getting muted.
Yeah, now it is fine, sir. Then okay. Yeah. Sorry for a stupid question, I think.
No, it's not a stupid question. It's perfect question. So that's why we are here. No, forget about it. So then there is one question. What is the minimum lag so far ever observed between the atomic pulse and its observation? No, during talking, reading from an atomic clock. I have no idea about this question. What is the minimum lag so far ever observed between the atomic pulses and its observation? Note down. Do you mean like what are the minimum, like let's say, inaccuracy between two atomic clocks? If that is what you are asking, then it has been observed few times 10 to the power minus 19. Actually, this slide I just kept, I was keeping these things. So this is, for example, at NIST, USA, these are two ytterbium atom clocks, neutral atom clocks. They compared for geodetic measurements, which I did not explain because of time. And there they have measured it few times 10 to the power minus 19. And that's the best so far. Does that answer your question? Yeah. Okay, so since there are no more, Utkarsh, you have further questions, or you can lower your hand then? So then the last part, I am talking about the experiments or labs that we are building at IUCAA. So this lab is called Precision and Quantum Measurement Lab, and the goals are quantum metrology, precision measurements, and quantum technologies. So this is, the lab is actually coming up. It's very new. It started few months ago, and then it's being built, and it will be filled up slowly. These are the people who are working at present, PhDs, postdocs, and interns. So in this lab, I'm going a little bit quick here. In this lab, we'll actually build ultra stable reference of laser photons. So lasers are not that stable. I mean, they are also changing over time, drifting over time. For making them ultra stable, we have to have a reference of optical atomic clock, and we want to build an ytterbium ion clock using trapped ytterbium ion. And I am going little quick. I already discussed about the ion clock, so not going into that detail. So this will have optical frequency comb, which will be referenced with respect to an ytterbium ion clock, and then it will have some other RF clocks also, and ultra stable cavity for stabilizing these systems. And then finally, this entire system will give me ultra stable photons, which are referenced with respect to optical atomic clock, and that can be used for these precision fundamental science experiments and so on. So this is not as simple as it is shown here. So everything you have to develop, particularly this optical atomic clock and these ultra stable laser systems, and integrating all these things together. It's a big job. So that we have started developing in the lab. I mean, simulating few things in the lab, and we'll develop slowly, and that can be used other than the fundamental science experiments for various other purposes, including like ultra precise detections of noises like in LIGO and so on, and then even calibrating the spectrometers. Those are used in like telescopes, let's say optical telescopes or UV telescopes, and so on. Then their sensitivity is basically limited by resolutions in spectrometers. So that can be done by improved by these techniques, and so on. It can also be used for quantum communication experiments and so on. Okay, this I am skipping, and this also I am skipping. And once, I mean, there are few labs, as I told you, in India who are trying to develop optical clock, 4 labs at least. NPL in Delhi, we at IUCAA, then ISSAA Pune, and then IIT Tirupati. So all these labs can be in future connected to do these fundamental science experiments. And as a precursor of these entire interconnecting experiments, our plan is between ISSAA Pune and IUCAA, these 2 clocks can be interconnected by phase stabilized optical fibers. And then strontium and ytterbium is a very good candidate. So we want to do these experiments in future. So basically, in short, the PQM lab is building this reference optical clock based on trapped ytterbium ion. Then they will work on these interconnecting experiments with ISSAA Pune. We are also planning to build the chip traps. So that will be used for building the compact atomic clock instead of lab-based clocks. So we don't have any plan to build compact atomic clock at this moment, but the chip trap we want to build, which is an important part to build the compact atomic clock. So maybe in the future, once we are successful in building this chip, we can either develop it to ourselves, or we can give it to IIT Tirupati. They can develop the chip clock, compact clock, and etc. And this is what is going on. So thank you very much. I am done. If there are questions, then I can take. Please let me know if there are questions. I don't see any. hand raise. So there are no more questions. Okay, then thank you for attending the lectures. Stay safe. Okay. Bye.